Good day, Dr. Isaacs. Today we will be presenting on designing Puerto Rico's power grid. Members of the group are Kyle Jeffrey, Najee Porter, Rajiv Smith, Kenelia Montague, Jordan Adams, Sanjay Daly, Joseph Gibson, and Shake Barrett. Let's get started. Firstly, let's start with the background of this design project. We went with the scenario that Puerto Rico was struck with a 7.2 magnitude earthquake that leveled more than half of the country's power grid. The power company of Puerto Rico then recruited a group of engineers to design and restore power to various communities on the island. The new power network that Puerto Rico is desirous of having is one that consists of 5 major load points and 2 generation plants. Shown right now are pictures of the damage done by this disastrous earthquake.
When constructing a power system, there are a few major components that need to be taken into consideration. 3 such components are generators, transformers, and transmission lines, which we looked at in detail in the literature review.
Power generators. These are machines which create electrical energy from mechanical energy and utilizes the principle of Faraday's law of electromagnetic induction. Generators consist of 2 main parts: the rotor, which is the movable component, and the stator, which is stationary. As the rotor spins, it induces an EMF within the stator windings, which produces a 3-phase voltage. Generators are classified based on the rotor component. There are 2 main types of generator classification: cylindrical rotor and salient pole rotor. Cylindrical rotor type consists of 1 set of poles, cylindrical in shape, and operates at speeds of 1,500 to 3,500 RPM, while salient rotor type consists of multiple poles and rotate at lower speeds of 100 to 1,500 RPM. Thermal generating plants. Thermal generating plants uses heat energy in order to boil water at extremely high temperatures to create steam, which is then used to move the prime mover of a generator, which is normally turbines, in order to turn the rotor to create electrical energy.
Moving now to transformers. Electrical transformers are machines used to transfer electricity from one side to another, facilitating a change in voltage without a change in frequency. These devices are considered static as they do not comprise of rotating or moving parts. Like generators, transformers utilize the basic principle of Faraday's law, which states that the EMF induced in a loop due to a changing magnetic flux is equal to the rate of change of the magnetic flux threading the loop. Transformers help to improve safety and efficiency of power systems by raising and lowering voltage levels as when needed. They are used in a wide range of residential and industrial applications, primarily and perhaps most importantly in the distribution and regulation of power across long distances. There are several types of transformers that may be used in any power system, but today we will focus on the power and distribution transformers. Power transformers are generally located at the generating level and transmission substations. Voltage is generated in low levels as it is more efficient and less costly to do so. Therefore, at the generating level, power transformers are used to step up low-level voltage to high-level voltage for efficient transmission to substations. At the transmission substations, power transformers are then used to step down high-level voltage to low-level voltage to be distributed to customers. Distribution transformers are used in distribution networks where they step down high-level voltage to low-level voltage to be utilized by customers. They are much smaller in size than a power transformer and may be found mounted on poles or the ground. These transformers employ the use of resin-impregnated paper and oil for insulating, cooling, and element protection purposes.
Transmission lines. Transmission lines are two-port circuits used to connect a generator to a receiving load over distance. These lines are made from metal alloys and are not insulated due to their height above ground level. They transfer electricity at high voltages and low current to reduce loss and are normally connected at each end by power transformers. The two-port network within the transmission line consists of network parameters. These parameters are resistance, inductance, and capacitance. These parameters also depict the amount of loss in the transmission line over distance. There are different types of transmission line, but the transmission line that was selected for our power system was the aluminum conductor steel reinforced transmission line, also known as the ACSR. This line was selected due to the following properties. It is cheaper, it is more flexible, it has good bending properties, lightweight, good conductivity, and good tensile strength.
Nadia Port here again. So let's continue by taking a look at a basic diagram of a power grid. Looking at the diagram, you will see that there is A, B, C, D, and E. A represents the generation part, B represents the transmission, C, distribution, D and E represents our end consumers. Generally, when we're talking about power grids, we split it into three main sections: generation, transmission, and distribution. Now let's go to the letter A first, generation. Now, don't be fooled by the name. We're not actually generating power, but the power that we're referring to is electrical power. And it's not possible to create or destroy energy, so therefore it's also not possible to create or destroy electrical power either. According to the first law of thermodynamics, it simply means we can only transfer from one form to another. So in order to get the energy, we'll need to find another source of energy and then convert that energy source into electrical power. An example of this source could also be the use of coal. With coal, you will have chemical energy burning in a furnace, then you get heat, then that heat goes to water, then steam, then that steam goes to a turbine. That turbine rotates and produces mechanical energy. That then goes to the generator, and the generator will then convert mechanical power into electrical power. As it relates to the transmission part, we're going to encounter losses. These will be due to the resistance of our conductors and also the heat that's generated when current flows through the conductor. As it relates to the size of the conductors, the larger the conductor, it will cost more, it will be difficult to handle, and it will generate less heat. But for the small conductors, it costs less, it's easier to handle, but it generates more heat. So, in transmission, really, the goal is to reduce current, to reduce the losses, whereas this is done by also increasing the voltage.
The requirements are designed in this project are load centers between at least 8 miles apart with total system demand of 400 megawatts, comprising primarily of load types: industrial, coupe, commercial, Las Perdas, residential, Vega, Baja, small commercial or residential, Las Cruces, farming communities, Mariana. Load transformers are required to have additional capacities for system expansion and under no condition be loaded above 75% of capacity. Transmission lines, like the transformers, should also have an additional capacity for increased demand. No generation unit to be loaded above 90% of its capacity. The host spinning reserve margin at all times for the system must be on average 25%. The considerations in designing the power grid are the type of transmissions line, type of generator, type of transformer. Voltage tolerances must be within the accepted normal range for power systems. The total losses should not exceed the acceptable limits for a transmission system. Location of load centers, allocation of power to load centers from generators.
Good day, Dr. Isaac. Roger Smith here. In playing my part for a design project which is based in Puerto Rico, I was given the task to therefore find a nominal voltage in Puerto Rico, which will further aid in determining the ratings of our transformer, our transmission line, and so on and so forth. So in carrying out my aspect of the one part of my aspect of the research, I stumbled across this diagram which it enlightened me a lot about the nominal voltages and how they distribute their voltages to their commercial areas, residential areas, and so on and so forth. So I therefore made the decision that our low side for our transformer would be 13.8 kilovolts and our high side for our transformer would be 115 kilovolts. So all the major components of our transmission lines or generators, and as I said before, our transformers were built around the parameters of this discovery that we found on the internet pertaining to Puerto Rico and the distribution, or rather the nominal voltage. On this line, it refers to the several parameters that were inputted into our generating and transformer units. It was noted, if you take a closer look, you notice that our generator only have internal sequence impedance, neutral to ground impedance. As for a transformer, it only has a zero sequence impedance. And these are just impedances that are required for our various devices for various reasons to protect our devices from any faults. If you note, a delta grounded star selection was made for our transformer for the sole reason of not allowing fault from the system transmission line to reach back into the generating unit. We all know that that is detrimental to the system. So this slide is practically just showing us the parameters of the selected units, or the selected parameters for the units that are used in our system, or impedance, series reactance and impedance, series reactance and resistance for our transformers were selected via the appendix of the book and prior knowledge from the labs that we have done before. In aid of justification for our Google Pro display of where our buses and generating units are located, this diagram plays that part and help in justifying or explaining to why we selected those areas. As you can see, our top right, where the population is most dense, where you have majority of commercial buildings such as hospitals, fire stations, police stations, water treatment facilities, and the list goes on. So one of our generators will be based in this area for obvious reasons, because as you stated in one of your lectures, that the need for constant power, or the likelihood for power to be cut at a certain area, should be low in these areas, especially in hospital areas. So we decided that why not just put a generating unit smack in the middle of where the population is more dense, where facilities are more dense, so we can provide constant power in the need or in the scenario of anything going wrong. So to our furthest to our right was our farming communities. To our left was our residential areas. Lower down was our commercial areas. And this is just to justify the areas that we selected for our loads and generating units.
A load has a combination of both active and reactive power. In this case, we'll be calculating the active power, and to find out how much active power will be distributed to each load center, we'll use the concept of ratios. These ratios were obtained from Puerto Rico's monthly sales, and for the residential load, it was 0.65, while the commercial was 0.642, and the industrial was 0.177. Residential / commercial load was assumed to be 1/13 of the total of both the residential and the commercial loads. This assumption was made because of the population density of the area selected for these loads. To find out the active power needed by each sector, first we have to find out the unit load. That is basically the load needed for the ratio 1:1. So to find this, all we did was to divide the total demand by the sum of ratio, and that resulted in us having 245.7 megawatt. So for finding the load, for example, for the residential area, then all we did was to multiply the ratio used for the residential load by the unit load, and that resulted in us having 159.7 megawatt. Same method where we times the ratio of the load by the unit load. Najee Puerto here again. So taking a look at the reactive power calculations of the design, we did a little research and came to the realization that residential communities have mostly single-phase equipments and industrial have three-phase equipments mostly. So therefore, places that use mostly three-phase equipments would use more reactive power, and therefore the power factor would usually be like under 0.95. So going on, we also found that a power factor that's less than 0.95 is in need of more reactive power. A power factor that is more than 0.95 is, it's good. And a power factor that is 1 is perfect, but what we chose to do was to use a power factor. Well, what we chose to do was to assume power factors for various sectors, but not to make them perfect, because we're dealing with a real life thing. So for the residential, the active power was found to be 159.7 megawatt. So by transposing into the formula of power factor is equal to cos of tan inverse Q over P, we would then transpose to find Q. So to find Q, we selected the power factor for the residential to be 0.98. And that resulted in a reactive power of 32.4299 megawatt. The same procedure was repeated for the other sectors, whereas the industrial used a power factor of 0.9, the commercial 0.96. The small commercial / residential 0.987, and the farming community using 0.99 power factor.
For the transmission lines, we decided to use the Martin ACSR, and this has a maximum current capacity of 1250. The reason why we chose a transmission line with this high current capacity is because we expect the load to increase over time. And we also decided that we are going to transmit at 115 kilovolts because Puerto Rico also transmits at this voltage. The first steps of the calculations we have done is to find out the apparent power rating for the transmission line. So we use the apparent power formula of 3 squared times VT times IL. The VT we used was the transmission voltage, which is 115 kilovolts, and IL would be the maximum current of the transmission line that we use, and that would be 1250. When the calculation was finished, that resulted in us having a rating of 249 MVA. This rating is important as it helps us to monitor the amount of current that is flowing through this transmission line at any one point, as it creates an operational range for the transmission line. This diagram represents a 3-phase representation of the transmission we are going to use, where each phase is 16 feet apart. Next, we will find the inductance of the line using the formula L equal 2 times 10 to the negative 7 times the natural log of the equivalent distance between the phases divided by the geometric mean radius. So when we find the equivalent distance between the lines, it was 16, and this is so because it is symmetrical, so the distance won't change. But if it was asymmetrical now, meaning to say dA was, for instance, 12, you know that the equivalent will be different. And the GMR was taken from the appendix of the book, and that was 0.0479. So when these values were calculated, the inductance was found out to be 1.1660392 micro Henry per feet. So the next step would be to convert this inductance from feet to miles. So we use the concept that 1 mile will equal to 580 feet. So when it times the 580 feet times the inductance, we got 0.0061569 miles per feet. So the next step would be to calculate the reactance of the line, and that can be easily found by using the formula 2 pi FL. And the frequency we used was 60 Hz, as Puerto Rico also uses 60 Hz. That gave us a result of 2.32102 ohms per mile. So to find the reactance for each line, all we had to do was to divide the reactance per mile by the length of the line. And to show this, we have a sample calculation which we use the line between generator 1 and the residential load center. And the distance between these two locations were 16.72 miles. So as a result, the reactance would be 0.138756. This table shows all the values we got for the reactance when we use the same methods as before. The resistance of the Martin cable was taken from the appendix, and this resistance was 0.0803 ohms per mile. And this resistance was chosen at 50 degrees because Puerto Rico is located in the Caribbean. So there's a high possibility that they will experience warm weather throughout the year. So to find the resistance for each line, all we have to do is divide the resistance per mile by the length of the line. And as before, we use the line between generator 1 and the residential load as example, where we got 0.004803 for the resistance of the line. This table is showing the resistance obtained for each line by using the method that was shown before.
Good day. My name is Sanjay Daly. Now, in continuing the presentation, this calculation shows the method used to calculate the per unit impedance of each line. This calculation speaks specifically to the Palo Seco generator 1 to the Vega Baja transmission line. Now, the actual impedance was already available, and we had to calculate the base impedance. We did this by squaring the base voltage and dividing it by the base power. It equated to 132.25. And the per unit impedance worked out to be 0.000036 plus imaginary number of 0.001046.
Alright, so taking a look at a summary of the initial power grid, we can now state the following. The nominal voltage according to the Puerto Rico Electric Power Authority was 13.8 kilovolts. The Paco Seco gen was set to output 170 megawatt and 345 megavar. The Prepper gen was then set to output 255 megawatt and 310 megavar. As it relates to the transformer, MVA limit of 600 megavolt ampere was initially selected as the parameter. Also, the reactance of the transformer was obtained from the appendix of the Power System Analysis and Design book by Glover. Also, the resistance of both the transformers were then assumed to be 0.0005 per unit. The resistance and reactance were also used as the fault impedance. As it relates to the transmission lines, MVA limit of 250 megavolt ampere was calculated based on the type of the transmission line being used. Codename Martin, with a maximum current rating of 1250 amperes. The voltage of the bus bars that the transmission lines were connected to, according to the Power Authority, were then found to be 115 kilovolts. And as spoken about at the start of the presentation, sure, we know that the goal of transmitting to reduce power losses is to have a high voltage with low current. So this will now be an illustration of the initial construction of the power grid. From here, you will see the generation, the system demand, and the system losses. The total system demand right here is 400.02 megawatt and 105.5618 megavar. As you can see, the generators were able to meet these demands. So, after doing the initial run of the circuit, we went on to fulfill the following requirements. The load transformers are required to have additional capacities for system expansion and under no condition be loaded above 75% of its capacity. Also, we went on to do to fulfill this, we went on to do the transformer rating calculations. So we did that for each of the generators. So we took into consideration the transmission voltage and also the maximum current of the conductor. Firstly, we calculated the S would be equal to the square root of 3 times the 115 kilovolts times the 1090.36 amp to have an MVA of 217.184. We also went on to find the maximum, which will have been 217.184 MVA divided by 0.75, which was found to be 289.579 MVA. The same calculation was done to the remaining transformer that was for the prepper generator transformer. It was also found to be the same values as the transmission voltage and the maximum current of the conductor was also the same. Looking at the illustration shown right now, you will see the hot spinning reserve margin that was obtained after the transformer's MVA limit was set to avoid loading over 75%. You will see that it was found to be 100.12 megawatt. In the next slide, Mr. Rajiv Smith will show the calculation.
One of the constraints I found that involved for a hot spring reserve margin being 25% on average. What this is saying? This is saying that in the scenario of an excess load being demanded by the system, the generating unit should be able to supply at least 25% of the normal amount of power that it would normally generate. The calculation show what follows, where both units combined should be able to provide an excess of 100.12 megawatt given any scenario which would cause an excess demand of the system. Below that calculation, you can therefore see where the total active power for both generating plants was calculated, where it was calculated to be 500.601. So this is saying that this is the maximum amount of power that both units should be able to generate without exceeding the hot spring reserve margin, which in our case 25. Below that, we have the calculation that displays the maximum power for the slack, where the minimum output for the slack bus would be 200 megawatt, which leaves the maximum power for it that could be generated in the case of the next generator being out or contingent. Well, in the future, my colleague will therefore go about the contingency study. But this would be the case where if there's an scenario where one of the generators, the next generator is supposed to fall out, the maximum amount of voltage or maximum amount of watt power that should be generated by that generator would be 300 in excess of the minimum output. Another constraint in the lab involved for us not to load our transformer above 75% of its capacity. Bearing in mind that the maximum load that can go on the system is actually 500 megawatt. So this diagram merely shows the output after the parameters were changed to facilitate the constraint of the transformer in our lab design exercise.
Resiliency test. What is a network resiliency test? A network resiliency test is ultimately a type of software testing that puts the system under a light, a medium, or even a heavy load to test the performance of the system under these type of load. Now, this type of test is very important as it shows the capacity at which the system may perform, or it shows even to a greater capacity the components that may fail being under such loads. This slide now shows the parameters of each generator. Now, before the resiliency test could be conducted, some reasonable coefficients had to be inputted into the parameters of the generator. Hence, we use the coefficients or the parameters given to us in the laboratory exercise to carry out the resiliency testing of this system. In conducting the resiliency testing under light stress or light loading, we observed that the total system cost was $3,292.76 per hour. Using a scale case of 0.2, it reduced the system demand to 80.0004 megawatts. In conducting the resiliency testing under medium stress or medium loading, we observed the system cost to be $4,503.01 per hour, using a scale case of 0.5 to reduce the system demand to 200.01 megawatts. Now finally, conducting the resiliency testing under heavy stress or heavy loading, we observed the total system cost to be $7,549.18 per hour, using a scale case of 1. This restored the system demand to 400.02 megawatts.
A contingency analysis is a hypothetical scenario created to analyze, evaluate, and prioritize its impacts on an electrical power system. For our contingency analyses, we removed both generators in separate instances, as well as single and multiple transmission lines to view the results. In this scenario, the Prepo Aguirre generator was removed from the system. From our test, we observed that this resulted in an overload at the transformer at the Palo Seco generator, as it was then solely providing power to the system. A similar result occurred in the analysis of removing the Palo Seco generator, as the transformer at Prepo Aguirre also experienced a lesser overload, picking up the slack of the missing generator.
A contingency study was done on the network using the transmission line between the Vega Baja and the Palo Seco bus bars, where the line was open. In comparison to the original network, it can be seen that the system remained efficient, with both transformers remained at 75% respectively. Another contingency study was done on the network in which all 4 transmission lines were disconnected. In comparison to the original network, it can be seen that the transformers exceeded the 75% limit, and the system at this point was overloaded, hence it was not efficient for the transmission of power.